Here's the 1, 2, and 3. I've got a vertical line here. I'm using the square root. I don't know what that point of intersection is. It's lower than 4. I mean, lower than 2, but okay, whatever. But this is the area, right? Oh, no, it's been shifted over. I'm sorry. It's not square root of x. It's square root of x minus 1 is here. So it's like that. Here's my area. So it says use isosceles right triangles perpendicular to the x-axis. Isosceles right perpendicular to the x-axis. Yes? So I'm thinking I'm looking like this. Isosceles right. I'm thinking that that's the base here that's sitting as part of, does that make sense? Yeah. Normally they will tell you the base of the shape sits on this. So I don't, what did y'all look at the answer? This one was not on there? Okay, well, good question. Apparently it's a lot easier if you use it as the base and not the hypotenuse, though, looking at that answer. So let's say that that's the base. This is the square root of x minus 1. So the base is square root of x minus 1. And since it's an isosceles right, that means this one is also square root of x minus 1, which means my area of just one triangle, 1/2 base times height. I wonder if that was defined in the beginning. It was not. That's interesting. Forms the base of it. If you look in the very beginning, a region bounded by something and forms the base of various solids. The cross sections of each solids are listed below. So they just define in the beginning as saying that the cross section is going to be the base of the triangle. I guess that's why we assume, but that was a lot of assumption there. Yeah. That's what isosceles means. Isosceles, two congruent sides. Yeah, so that's why. So this would be 1/2 x minus 1. Now I just integrate, right? The integral, what am I going from? 1 to 3 of the square root of x minus 1 dx. And this one said even use your calculator to, what is it? I'm doing it today. Of course it is. Use your calculator to evaluate. So we'll just use the calculator to plug in and find out what it is. This would be a fairly easy one to evaluate by hand. If you did, because I have 1/2 x minus 1/2 from 1 to 3. So that would be 1/4 x squared minus 1/2 x. I'll evaluate it from 1 to 3. But you can use your calculator since it told you to. Does that make sense? You're trying to do it in your head. 1/4 minus 1/2. Doubled, so 6, 9 minus 6 would be 3/4 minus 1/4 minus 1/2 would be -1/4. Did y'all do the semicircle cross sections perpendicular to the y-axis? Mm. Of course you did, right? Let's do it, because that one seems fun. first of all, I need to know this point, and I need to know this point because I'm going to do it with respect to y, so I need to know how high up to go. So since I go with respect to, we're just going to pretend like I didn't do any of that. Oh. Okay, well, let's do it together. How about that? Let's do it together. Okay. Gosh, I would have just failed this one altogether. Okay. Y is the square root of x minus 1, which means x is y squared plus 1. Great googly moogly. Get together, Stacy. Which means this distance is, I go all the way over to 3 and I subtract y squared plus 1. And that's going to be the diameter of my circle. Does that make sense? Does that make more sense? Because I'm going with respect to y. Okay, so now the radius is a half of that, right? And I'm just going to clean this. I'm going to say 2 minus y squared. So the radius is 1/2 2 minus y squared. Yeah, that's negative. I said minus y squared minus 1. So now I get the area of my semicircle is 1/2 times pi times radius squared times another half, right? No, yeah, half. You see, I'm doing half because it's a semicircle. It's not pi r squared, it's 1/2. 1/2 pi r squared. So the area of a circle is pi r squared, right? I don't know. I'm saying so much stuff. I might even be telling you the area of a triangle, and you don't even never know what's going to come out of my mouth this morning. All right, so half pi, and then I need to do 1/2 2 minus y squared. Gross. So I'm going to do the integral from 0 to what? Square root of 2. I'm going with respect to y, remember, so I'm bottom to top. This point right here. I did. I put 3 in here. Because I know x is 3, that's a vertical line at 3. I'm probably going to take this pi over 2 and put it on the outside. I might even make that 4 times 2, 8, and take that outside too. That would be 1/4 times pi over 2, which would be an 8. And then inside have 2 minus y squared squared. I had to square it first and then multiply it. And then I put this on my calculator. I don't know what you get. $1.1847. Is that what you got too? Oh. I was gonna say that's the same thing they got. They didn't pull anything out to start with. They went 0. Oh yeah, they did pi over 8. There's their pi over. Yeah, I think that's what happened because we did. We simplified here. So let's see. So then pi over 8 times the integral y1 x from 0 1.1847, yeah. I felt pretty confident about that one, but then you never know. Just never know. I think cross sections are harder than revolution, in my opinion. But and anytime you change variables and you go with respect to y instead of x, it gets sticky. That's the answer. 1.1848. Is that what y'all got when you plugged it into? Good. For 9. First section, I'm assuming. You're going with respect to y. All right, so I got y equals square root of x. I'm going to take my time through this one so that I do it right instead of. Oh, rectangles whose height is 6. This is number 9. Yeah. First section. All right, so I've got 1/3 x would be 0, 0. I mean, they give you the graph, but and then it intersects. It comes back and does this. So I'm looking at this area. This is square root of x. This is x over 3. And I think I'll go ahead and find a couple of things before I even get started. I'm going to find points of intersection. And since I know that I'm going to be doing it in terms of y, I'm going to go ahead and solve for x on both of these as well. So I'm going to say that y squared equals x and that 3y equals x, just so I can reference those should I need to. And I'm going to find this point of intersection. So where does the square root of x equal x over 3? It should be 2 places, right? It should be 0 in one other place. So 9x equals x squared. X squared minus 9x equals 0. So x times x minus 9. That should be when x equals 9. That looks like it on your, but whatever. At x equals 9, what's the value of y? 3. It should be the same thing no matter which equation you plug it into, because that's where they're the same. Does that make sense? Okay. Now let's do the problem. It says rectangles. Now, first of all, how do you find the area of a rectangle? Length times width, or length times height, one or the other, right? Well, for this particular one, it says the heights are always 6, so your height is constant on these. So all that means is what's changing is, oh, we're going the other way, aren't we? This is changing, but they're still standing up 6 each time, okay? So it means my area is going to be 6 times whatever that width is here, and this is that width. Does that make sense? Everybody understands what the problem's actually telling? Okay, so what I need to do is find out what is that width. How do I find that width? And so this is kind of like that area under a curve thing with respect to y. So I'm going to say, well, this distance, if I take this whole distance and I subtract out the whole h, so take the w whole minus the whole h whole, right? Does that make sense? You see what I'm saying? We're still kind of starting to get into what we'll do with revolution. Then it'll give me what's left here, and that'll be the width of my rectangle. Well, what is this all the way over? Three y, right? Because I'm doing it with respect to y. So I'm going to do, because it says x equals 3y. I don't want the height, I want the length. The y would give me the height, the x is going to give me the horizontal span. So my width is going to be 3y, but then I have to subtract out this little distance, right? So what is that little distance? Y squared. Do y'all see why? From here to here is 3y. From here to here is y squared. So I take 3y and I subtract y squared. Does that make sense? Y'all sure? All right, so now remember, if I can nail down that area formula, the volume's a piece of cake from there. So what's the area of, yeah. Yes, that's the right minus left. That's exactly what it is. So what is the area of my rectangle? 6 times 3y minus y squared. Now I'm good to integrate. Once you get that part, it's downhill from there. Are y'all okay? Sure. So now I can do the integral, and again with respect to y, so from the bottom to the top, so from 0 up to what? 3, because I'm taking the y value, not the x value. And then I just throw that area formula in there. 6, 3y minus y squared. Well, what I would do, I would just pull that 6 out here. But you could if you wanted to. I don't know if they told you to do this with a calculator or not. This is a pretty easy antiderivative. 3 over 2 y squared minus 1/3 y cubed. I'm writing too fast for it. From 0 to 3. So I'm going to plug the 3 in. Anytime 0 is one of my bounds and everything has a variable on it, it makes it a little bit easier for me to evaluate. Minus 0. 9 times 3 is 27. 27 over 3. Did I do that right? Ugh, now I need a calculator. I would stop right there. If it's an FRQ. Huh? What's 27? Is it? Times the 6 too? Oh, okay. Yes, no, maybe so? What else? Y'all need a break a second? Because you know it's going to get better. Yes. This and one more and we're done. So far, we've been taking cross sections of shapes. Like if we could literally take a saw and cut them into these itty bitty pieces, slices and slivers, and then integrate from there. But now we're going to talk about what if we rotated shapes around an axis or even around a line itself. So here's what I'm talking about. Let's say I like x squared. It's kind of easy to see what's going on. Let's say I took this shape from 0 to, this is x squared, from 0 to, I don't know, 2. And I have this shape right here. And I said that shaded area I take and I rotate it around the x-axis 360 degrees until it comes back on itself. What kind of shape am I looking at? It's like it's almost like a funnel or a cone or something. Like it starts out itty bitty and then it kind of grows and it looks, I think about like a horn maybe or something. Does that make sense? Or, are y'all ready for this? If this was my shape sitting on the x-axis, right? And I started to rotate it around, watch what happens. This is my shape. Don't y'all love it? I've saved this just for that, just for this one lesson. Okay, but that's what happens, right? As I rotate around. Does that make sense? So then if I took cross sections every single time, think about if I had this shape, I don't break now, I've used this for years, and I sliced, every single slice is going to be a what? A circle. So every single one of these, that's why I call it a disc, volumes of rotation using disc. They're all going to be circles. So I'm not going to have to determine a shape, right? Because they're all going to be circles. So we're always going to be using the pi r squared. This doesn't matter because it's going to follow along this path, but I'm taking circles out. But what's happening is, and if you think about it again here, this is my curve, right? And I'm wrapping around. So if I cut it, right, I have a diameter here from top to bottom, but if I look, this is my radius, right? So this is my radius. I don't have to cut it in half anymore because it's not a diameter. I'm not taking a semicircle or a circle out of that. That is my radius because it's wrapping around. Does that make sense? So for this one, my radius is x squared. Pretty easy. Okay. So if I wanted to know, for example, this one, what's the volume if I rotate this around the x-axis from 0 to 2, what's the volume of my solid? Well, my volume would just be, remember, it's pi r squared, so the area of one circle would be pi. My radius is x squared, pi r squared, right? So what I'm integrating is from 0 to pi x. So on these, a lot of times what you'll see is that volume equals, you'll pull the pi out, go from A to B, and then it's just the radius squared, whatever that radius is. I like to do it the same way we've done cross sections because we've already learned how to do the cross sections. So if you understand that it's nothing more than just the area, then that helps you understand. Yeah. Sometimes they will. If you get like a point for setting up the integral and you don't have it, you wouldn't get that point for setting up the integral. We'll practice with them and I'll dock you a point. It's kind of like, remember whenever we had like the plus or minus in front of the square roots and I was like, y'all will do that one time and I'll dock you points on it and you'll never forget again. Y'all never forgot again. You'll remember, it'll start coming natural to you. We'll do semi practices with it. Right now I'm just been trying to just cram the concepts and then we'll get with the practice and the perfecting all that where you get every possible point you can. All right, y'all ready for a real example? I mean, that really was a real example. But... well, whatever you get here, I mean, you go through the same way we've been doing. So pi times the integral from 0 to 2 of x to the 4th dx, which would be pi times 1/5 x to the 5th from 0 to 2. Whoa. 2 to the 5th, 2, 4, 8, 16, 32. We just double every time. 32 pi over 5. I'm so happy to finally be here. This is probably my favorite lesson in all of calculus. I love volumes of rotation. Why, I don't know. But I do. Let's rotate one of these bad boys. I like to visualize the shape that's going to happen too, right? Because you never anticipate what the shape is going to look like. And then you, okay. We can also rotate these around the y-axis, the x-axis, or even around a line. But we'll do lines later because then that'll have a hole in the middle. That's all. That's Monday. Let's see. This is number 10. Find the volume of the solid generated by revolving the shaded region about the given axis. It's got a pretty little pink line drawn right here. That's it. That's all I know. This is a calculator. I don't trust their calculator or non-calculator gobbledygook. Tell me what you think. That's the radius. You're exactly right. That's the radius of my disk. Sine x, cosine x. So what's the area of my circle? Or pi sine squared cosine squared, either or. I still have one more slight problem. What is that? I don't know what that is. I don't know where to stop it. I can graph it. Do I know where sine x cosine x equals 0? When either one of them equals 0 is when. So where's the first place after 0 that either one of them equals 0? Pi over 2. Does that make sense? As long as one of them is 0, it's going to equal 0. The first place that happens as I click around is pi over 2. Well, set it up. What's the volume? The integral. From what to what? 0. Pi over 2. Of pi, and I'm going to put this pi out here because it's always a constant and it's always there. Sine squared cosine squared. This is probably why this is a calculator. I don't know the antiderivative of sine squared cosine squared. I could do a u, but then even with a u, I get more. Yeah. They got an exact answer for it. I can't use sub this, can I? If I did cosine squared, if I did cosine. No, that well they have. You know what I bet you could do? I don't know. We'll just put it in our calculator. We'll put it in the calculator. What'd y'all get? The whole thing with the pi or without the pi? 0. Yes. All right. Yes or no? What do you think about a disc? Y'all ready to crank it up a little bit? Let's do. Pick one for me to do. Y'all decide. From the practice, the 1 through, that's what I should have just printed. I shouldn't have printed that first page. It's okay. 1 through 10, pick one. Or 11 if you really want. 3? Henry says 3. Oh, it's a revolve around the y-axis too. Nice job, Henry. Nice job. X equals 0, y equals 0 just tells me that I'm in quadrant 1. Number 3. 8, 9. Number 3. They should have each, you shouldn't, yeah, I ran them wrong. Yeah. The practice, don't do, yeah. All right, so I'm first quadrant up 2, down 1 over 1, 2, down 1, oops. Here's my shape. This is y equals negative 1/2 x plus 2, and since it tells me that I'm revolving about the y-axis, I am going to go ahead and solve this for x as well. Subtract 2 multiplied by negative 2, so I'll get negative 2 times x minus 2. Y. Ready, Freddy? Even though this looks like a triangle, remember I'm rotating it around. What shape is this going to look like? What's the three-dimensional shape it's going to look like? Yes, with the point at the top, right? If it went like this and rotate around, it'd look like one of those, you know, you drop your penny in and it spins around and around like a funnel. But this would be the opposite. So this is going to look, this is just literally going to look like a mountain. Yeah, a pyramid, a rounded pyramid. All right, we need a radius. And this is my radius, yes? Well, what is that distance? The x equals part, right? That's my 2, negative 2 times y minus 2. Well, but remember, as it wraps around, if I cut it in pieces, every piece is going to be a circle because it completely rotated around 360 degrees. So what's the area of my circle? You can. I would probably make this 4 pi times y minus 2 squared. Because I'd probably, remember this goes here and here, and then I'd just pull that outside if it were me. And now I am ready to integrate. What are my bounds on my integral? 0 to 2. Why am I going to 2? Because I'm going up because I'm doing with respect to y, not with respect to x. Now I do my area, which is 4 pi times y minus 2 squared dy. And of course, if I'm using my calculator, I could change that to x if I needed to. I'm going to FOIL this out because I'm a glutton for punishment. Not always, no. So this would be a non-calculator because it says leave your answers in terms of pi. Most of these are usually non-calculator on rotations like this. So 4 pi times, I've got 1/3 y cubed minus 2y squared plus 4y, going from 0 to 2. The 0 is nice because I don't have to really do anything with that one, so I'll have 1/3 times 2 cubed minus 2 times 2 squared plus 4 times 2. 8/3. 8. 8. I got 32 pi over 3. Is that what y'all got? Let's rotate around something else then. Calm down. I know y'all are excited, but just hold it in just a little bit longer. Yeah. Yes, but we'll go around lines with no holes. You'll see what I'm talking about. So flip over to 810 and let's look. I'm going to look at the back, at the practice on the back. Let's do an easy one to start with because we haven't gone around a line yet. We'll just start with number 1. Who's short in 810? Oh, Henry. That's okay. I got one for you. I think they'll slide it. All right, so this says that y equals 3 minus x squared. And y equals not 1 but 2. And we're revolving about the line y equals 2. Number 1 on the back. Oh, you're right. When I gave Henry mine, I didn't have the other one flipped over. Okay, let's graph everything first and let's look at what's going on. 2 minus x squared, that's upside down parabola shifted up 2, right? Upside down parabola. And then the line y equals 1. What kind of line is y equals 1? That kind of line, right? Mm-hmm. Now, I'm rotating around this line, not the axis, okay? So I'm taking this. I'm not rotating around the x-axis. I'm rotating around this. So my shape is still going to be solid. Remember, all of these, finding the equation for the area is the hardest part. So determining what I need and where. So because I'm rotating this way, that means this is going to be my radius. Do you agree? Now, Monday, we'll take this and we'll rotate it around the x-axis so that there's a hole in it. But here, there's not a hole. All right, so I need this radius. Just that shaded part up top. Yep. It's doing the same thing as if this was my graph and there's my x-axis and I rotated that. It's doing the same thing. Yeah, yes. And it's actually going to look very similar to The football. Where'd it go? Right, because that's close to a parabola. So it's going to look very close to that whenever it's three-dimensional. So yes, egg-shaped almost. All right. What's the radius? Top minus bottom. You're exactly right. Top minus bottom. How do I know, first of all, because it gave me this y equals, how do I know that I'm doing it in terms of x and not in terms of y? Because they gave me y equals 1. That's a y equals equation. If I'm rotating it this way, the way like a wheel turns, that's with respect to x. If I turn it this way and start rotating about the y, that's in terms of y. You see the difference? Okay. It tells you, so this said rotating about the line y equals 1. So if this is y equals 1 and I rotate around that line, then I've got to flip it over this way. All right, top minus bottom, right? So 2 minus x squared minus 1. Yes. Yes, because this shaded area all the way up to here is 2 minus x squared, right? But I got this empty space here I need to take into account. Y'all okay there? All right. Let's find the area then of my circle. Pi r squared. Broke the cardinal rule there. I didn't find my intersection points first to know what I'm going from. Is it negative 1 to 1? That's the y value, but what's the x value there? So when y is 1, what is x? So I could, yeah, it's 1. Plus or minus 1. Right? Y'all follow me? I know you could look and tell, and I know that you knew from those, but if you had a more complicated equation, set them equal and find, right? Are y'all following me? Okay. All right, so volume, negative 1 to 1, or 0 to 1 doubled. Some of you like to use the symmetric. 1 minus x squared squared. I've got this pi I'm going to throw on the outside, dx. Does it say leave it? Okay, leave it. Does that make sense? You will encounter a lot of times whenever you get on FRQs and stuff and it says, find but do not evaluate the integral that gives the volume of blah. Because it's especially if it's a non-calculator problem, they just want to make sure you can set it up. Tell me what you think. It's fine.